Hello, my name is Benjamin von der Schmaan, and this is my ESE 403 final examination YouTube video for problem 8. My teammates were Andrew Montgomery and Daniel Lee. So to start, we're gonna look at problem 2. Now, problem 2 starts with providing us with a linear programming model along with the corresponding final set of equations yielding the optimal solution. Now, part A asks us to identify the optimal solution from the final set of equations. We find that the optimal solution is x1 equal to 5/3, x2 equals to 0, x3 equal to 3, with the z value of 17. The right-hand side of the cost function gives us our z value, while the right-hand side of the remaining equations gives us the values for x1, x2, and x3. In part B, we construct the dual using the simple rules for going from the primal to the dual. This involves translating the problem into the dual using the signs of the primal constraints and the decision variables. And then we move on to part C, which asks us to identify the optimal solution of the dual from the final set of equations and then confirm this solution graphically. And so looking at the cost function, we see that the optimal solution is y1 is equal to 1/5 and y2 is equal to 3/5. Then we graph each of the constraints of the dual problem and identify the corner point feasible solutions, finding that y1 equal to 1/5 and y2 equal to 3/5 is indeed the optimal solution. Part D switches the original problem, which forces us to construct a new dual formulation. We find that the previous optimal solution violates the second constraint, 2y1 plus 3y2 is greater than or equal to 3. Thus, the previous optimal solution is no longer optimal. Part E uses the fundamental insights provided in section 5.3 to identify the new x2 coefficients in the final set of equations. So looking at the equations for the fundamental insights found in section 5.3, we formulate a 2x2 matrix using coefficients for x4 and x5 in equations 1 and 2 in our original final set of equations. Then we multiply this matrix by a 2x1 matrix composed of the new coefficients for x2 as specified in part D in the linear programming model. Once we multiply them, we get the new x2 column to be a 2x1 matrix with values negative 1/3 and 4/5. Now, part F again switches the original problem and forces us to construct a new dual for the problem. We find that the previous optimal solution violates the fourth constraint, which is 3y1 plus 2y2 is greater than or equal to 2. Thus, the previous optimal solution is no longer optimal. Similar to part E, we use the fundamental insights in section 5.3 to identify the coefficients of x new in part G. So looking at the equations for the fundamental insights found in section 5.3, we formulate a 2x2 matrix using the coefficients for x4 and x5 in equations 1 and 2 in our original final set of equations. Then we multiply this matrix by a 2x1 matrix composed of the coefficients for x new as specified in part F. Once we multiply them, we get a new x new, or we get the x new coefficients to be a 2x1 matrix with values 1/3 and 1/5. Now we move on to problem 4. So question 4 asks us to use the MIP branch and bound algorithm presented in chapter 11 to solve the problem of maximizing z equals 20x1 plus 10x2 plus 25x3 plus 20x4, subject to the constraints given, as well as constricting x each of the decision variables to be integers. So we begin first by using the simplex to find the optimal solution of the equivalent LP relaxation problem. Using software, we obtain the optimal solution of x equals 2.13, 0, 3.73, 3.07 with an objective function value of 97.33, which we know is an upper bound of the integer solution of the original problem. The algorithm begins at iteration 1. We choose x1 as the first variable to branch on creating two subproblems. X is less than or equal to 2, and x is greater than or equal to 3. Solving the LP relaxation for both subproblems yields solutions of x equals 2, 0, 3.71, 3.14 with z equal to 195.7, and x equals 3, 0, 5.25, 0.25 with z equals 196.25. Both of the subproblems fail the fathoming test, so the algorithm continues. At iteration 2, we have 4 subproblems to consider, 2 associated with each of the other previous subproblems. In this iteration, we branch on x3 as it is a new variable, as it is the new next variable with a non-integer value. The four subproblems have x3 less than or equal to 3, x3 greater than or equal to 4, x3 less than or equal to 5, and x3 greater than or equal to 6. Solving these yields the following. Subproblem 1.1, 1.2, 2.1 all produce feasible solutions and fail the fathoming test, while subproblem 2.2 is unbounded and is fathomed by the tests. Their x values are 3, they are 3, 0, 4.5, and 1. At this step, we need only to branch on the subproblem with the highest function value, which is 2.1, and we continue. On iteration 3, we have two final subproblems. x4 is greater than or equal to 1, and x4 is less than or equal to 0. Solving these two final subproblems yields two solutions, both of which are feasible, one of which is optimal, that is subproblem 2.1.2, as indicated on the PDF page, with x equal to 3, 1, 5, 0, all integer values, and a z value of 195. And that concludes problem 4 of applying the MIP branching and bounding algorithm. We move on to problem 6. So in question 6, we are asked to maximize the following convex programming problem. F of x is equal to 2x1 plus 3x2 minus x1 squared minus x2 squared, subject to x1 plus x2 is less than or equal to 2, and the standard non-negativity constraints that we have seen throughout the course. So part 1, to use the KKT conditions to derive an optimal solution directly, we must first solve the following equations on the left to get the initial KKT conditions. And so these conditions are found in the book. I won't read them all off individually, but we're going to get these conditions. So once we have these eight equations, we can simplify them further. So first we take conditions 1 where j is equal to 1 and 1 where j is equal to 2 and add slack variables to change the inequalities to equalities. After looking at the set of equations, we see that equations 2 for j is equal to 1 and 2 for j is equal to 2 can be simplified. It is easy to see that x1 star x1 times y1 must equal 0 and x2 times y2 must equal 0. Equation 4 can also be simplified in a similar manner, yielding u times y3 is equal to 0. Combining these three equations, we get the complementary constraints x1, y1 plus x2, y2 is equal to u times y3 is equal to 0. And the following set of constraints yields a solution x is equal to 0.75, 1.25, and u is equal to 0.5. So now part B, the additional complementary was calculated above from equations 2, j equals 1, and 2, j equals 2, and 4. The linear programming problem to solve here it's a minimization. We're going to minimize z is equal to z plus 1, or z1 plus z2, subject to 2x1 plus u minus y1 plus z1 equal to 2, 2x2 plus u minus y2 plus z2 equal to 3, and then lastly x1 plus x2 plus y3 is equal to 2. All of the variables are non-negative. Now in part C, we show the solution derived in part A is optimal for z is equal to 0. We plug in our optimal solution in the equation. Simplifying yields 0.75 y1 plus 1.25 y2 equal to 0. And the only solution is y of I is equal to 0, which implies z of I is also 0, proving that our initial solution is indeed optimal. And y of I and z of I, of course, corresponding to the variables that take on y and z. So moving on to part D, we set up the problem as formulated in part B to be used in the modified simplex method below. We choose spot x1, x1, and perform the necessary steps giving us the second tableau in this step. We choose x8, x2 as the variables to calculate on. In the third tableau, we choose x5 and x3. And in the final tableau, we find the optimal solution to be x1, x2 to be 0.75 and 1.25 respectively. So this simplex method following the rules we learned in class. And so now we move on to part E, which is where we perform a two-stage dynamic programming problem with where we have two different stages. In stage 2, our cost function that we're looking at is f2 star is equal to the max of 3x2 minus x2 squared. S2 can take on the values of 0, 1, or 2, with x2 taking on the values of 0, 1, and 2. We calculate that the f2 function values of 0, 2 or the f2 function values are 0, 2, and 2 respectively for the s2s that we have. And then in stage 1, our new function is going to be f1 star is equal to the max of 2x1 minus x1 squared plus f2 star, which is kind of our moving backwards motion that we do. Kind of our we start our 3 2 1 or 1 2 3 3 2 1, kind of that dance that Professor was talking about before. But yeah, when we solve that table, we see that S1 has the values of 2, 2, or 2, and X1 takes on the values of 0, 1, and 2. We calculate the F1 function values of 2, 3, and 0 respectively, and this identifies the optimal integer solution, working backwards as x1 star is equal to 1 and x2 star is equal to 1, gives us a z value of 3. And then lastly, we have part F, which asks us to solve the convex problem using Excel. We begin by formatting the sheet. First, and this is not on the PowerPoint, but I'll still explain how it was done. So we begin by formatting the sheet. First, under variables x1 and x2 in cells B3 and C3, we will contain the values they take on in the function. The equation coefficients are written as well. And cell A5 is where the associated equation is written to calculate the value of z. So our cost function, the equation is we multiply the corresponding cells together. We notice that cells B8 and C8 simply reference cells B3 and C3. Cell A9 contains the function B8 plus C8, and then the Excel solver set to GRG nonlinear programming and max cell A5 with the constraint A9 is less than or equal to D8. It solves the optimal solution of x is equal to 0.75 and 1.25, which confirms the solution that we found earlier just using an Excel program. So thank you for listening. I hope you enjoy my explanation for the 3 problems you asked for. It was a pleasure being in your class, and have a good rest of your day.